Bienvenidos a este aquarium que es vuestra casa y os acogemos con un cariño extraordinario porque verdaderamente estoy impresionado de tanta inteligencia, tanta sabiduría que tenemos aquí concentrada en este aquarium. Bienvenidos todos, bienvenidos. Bueno, lagun maiteok. Me parece que fue María Montessori la que por primera vez puso en forma de gritos las exigencias de los educandos. ¡Enseñarnos a actuar! Gritaban y gritaban los niños dentro de la feliz, aunque convencional, idea montessoriana. Y la llamo convencional porque es evidente que los niños no conocen más gritos que de las rabietas o del entusiasmo por su contento extraordinario, y que por consiguiente no parecen capaces de proferir gritos tan intencionados como el que me sirve de base para este comentario. ¡Enseñarnos a leer! Gritaban y gritaban los niños con razón, no pocos de los niños de 5 a 6 años, porque padecemos de dislexia. Sabemos leer mecánicamente, pero no sabemos extraer las ideas de lo leído. Y saber extraer las ideas de la lectura es el fundamento indispensable para saber estudiar. Enseñadnos a trabajar y a estudiar por nuestra cuenta, podrían decir los adolescentes de 12 a 14 años, porque no solo debemos ser considerados como sujetos pacientes de la cultura, sino también sujetos activos. No os contentéis, por consiguiente, con cortar bellas flores para ofrecérnoslas. Enseñadnos también a cortarlas y también a cultivarlas. Y desde luego, no os empeñéis en suministrarnos el alimento cultural totalmente triturado. Algo así como si hubiese pasado por un turmis docente, porque las papillas, que son indispensables cuando se carece de dientes, no tienen sentido cuando la dentición es completa. Y es que en el aprender sucede lo mismo que en el andar. Es decir, que llega un momento en que las andaderas o los tacatacas se encuentran de sobra. No nos atiborréis de erudiciones, porque no nos sentimos tan necesitados de información como de formación. Que aprendamos a discutir con serenidad, es lo que necesitamos, y a expresarnos con exactitud, y a redactar con precisión, porque bien pertrechados con tales instrumentos el porvenir cultural nos pertenece. No nos parece innecesario el interés extrínseco por la ciencia, interés que se fundamenta en las acciones y premios. Pero necesitamos también el interés intrínseco, porque es lo único que nos proporciona la curiosidad intelectual, que es el principio de la sabiduría. No somos número de una grey, sino personas con sus notas individuales, y por consiguiente no deberíamos ser tratados según los mismos patrones. No queremos fórmulas docentes estandarizadas, sino peculiaridades, es decir, perfectamente bien adaptadas a la situación psicológica de cada cual. Y tener además en cuenta que mientras no logréis establecer un afectivo puente entre vosotros y nosotros, nuestras enseñanzas resultarán inútiles. Y es que en pedagogía, lo mismo que en tantas otras actividades de aspiración social, la tercera y definitiva palabra es la palabra amor. Es la palabra amor. No confundáis la educación con la nueva instrucción y mucho menos con la domesticación, porque la domesticación solo se sojuzga y por la mera instrucción solo se culturiza. Por la educación, en cambio, se forma y se desarrolla al sujeto en todas sus facultades. De donde se deduce que estas exigencias podrían muy bien repetirse lo que se decía de las ideas universales en la vieja controversia entre nominalistas y realistas moderados, a saber, que tales exigencias tienen realidad en cuanto a aquello que demandan, aunque de ninguna manera la tengan en cuanto al modo de demandarlo. Y nada más, mis queridos amigos intelectuales sabios que tenemos aquí en el Aquarium, bienvenidos. Y permitidme que diga, ¡vivan los sabios! Y vivan los profesores, y vivan los niños, todos, ¡viva! Adelante. Os envío un fuerte abrazo a todos. Va a ser cada batondilla. Es que ricasco. Bueno, a continuación toma la palabra, bueno, que no ha venido, ¿no? Bueno, toma la palabra don Pedro, que este no ha venido, que tenía que venir, que era viceconsejero de Universidades e Investigación y presidente del BCBL, don Manuel Carreiras. Tampoco ha venido, ¿no? Bien. Hay que ponerles falta, ¿eh? Bueno, entonces te dejo aquí esto para esto.
Muchas gracias.
Es carricasco, señor. Gracias.
Ongi Torri, Arratsaldeon, buenas tardes a todos. Gracias por haber venido. El viceconsejero llegará, pero llegará para clausurar el evento, ¿no? Bueno, yo ante todo quiero darles las gracias por estar aquí con nosotros para celebrar este nacimiento, esta ceremonia de apertura del Basque Center on Cognition, Brain and Language, que es un centro que probablemente hayan leído sobre él en los periódicos. Es un centro que acaba de nacer, que está dedicado al estudio de la adquisición, de la comprensión, de la producción del lenguaje, de lo que sucede en nuestro cerebro y en nuestra mente cuando realizamos esa serie de procesos. Quisiera dar las gracias en primer lugar a nuestros patronos que han hecho posible esto. Ha sido promovido este centro por el gobierno vasco y a su vez tenemos 4 patronos. Tenemos a Iker Basque, la Fundación Vasca de la Ciencia, tenemos a Innovasque, tenemos a la Diputación de Guipúzcoa y por último tenemos a la Universidad de La Laguna, de la Universidad del País Vasco. Esta de La Laguna. Bueno, y sin más dilación, yo creo que ya tienen suficiente información sobre el centro. Tenemos hoy con nosotros para esta ceremonia de apertura a Mike Posner. En los folletos que ustedes tienen, tienen ya una biografía de Mike Posner. A mí no me queda mucho más que añadir, simplemente decirles que es una entrañable persona, un entrañable profesor. Es de esos profesores que los alumnos de psicología ya leen en los libros, entonces creo que no hay mayor tributo para un investigador que aparezca en los libros de texto que comienzan a leer los estudiantes de primero. En fin, ha sido galardonado recientemente con la medalla de la ciencia de Estados Unidos y tiene entre sus méritos un montón de premios y un montón de reconocimientos. Sin más, yo creo que es momento ya de escucharle para que nos deleite con su charla de hoy, cómo la educación modela el cerebro. Muchas gracias, Mike.
Well, thank you very much, Manuel, and also all of you for coming. It's a great pleasure to be here in San Sebastian. It's a beautiful city. I don't know exactly how the director organized this beautiful weather, but I'm most appreciative coming from a place that is quite rainy itself. I'm also very appreciative of having a small role on the advisory council of this magnificent new center that's going to be, I'm sure, very influential in the worldwide effort to understand brain mechanisms and apply them for the betterment of children. This center, of course, will be very concerned with children in the Basque region, but their contributions will go well beyond the Basque region to help in the betterment of children everywhere. Studying problems such as how parents can help guide their infants in the preschool years and how preschool education can help with the language skills that are necessary obtained during schooling. We're going to be talking about this organism, the human infant, and their brain and how it's molded by experiences. Currently in the United States, there is a great deal of interest in applying really what little is known about the shaping of the human infant brain to the very formidable problems of education. This man, Geoffrey Canada, has developed a program in this part of New York City called Harlem, called the Harlem Children's Zone. And its goal is to bring children whose upbringing may have been somewhat deprived up to the same level as their peers in other parts of the city and the state. Recently, there's been a book written by the New York Times correspondent Paul Tough about Geoffrey Canada and the Harlem Children's Zone called Whatever It Takes. And a little quote from this book from Geoffrey Canada as reported by Tough. It was so clear there was this body of information out there. Everybody agreed on the best practices. If you have a child who is 3 months old, we know exactly what you ought to be doing with that child. When your kid is 9 months old, we know that too. Non-debate. We don't need any more research. We don't need more studies. But in our community, that is the community of Harlem he was talking about, no one was talking to our parents about this body of knowledge. And what Tough and Canada meant by the body of knowledge was the findings that middle-class children heard many, many more words in their upbringing than those of the poorer classes. And often the speech directed toward children was much more in the vein of tuition than in the vein of simply controlling their behavior and telling them when they were inappropriate. Of course, I think that there is much to be admired in the Children's Zone, the Harlem Children's Zone. And President Obama had promised as a candidate for president, and you know he tries to fulfill all his promises, he promised as a candidate for president that he would generalize this to 20 places and help Canada and others to inform parents of the importance of their child's early years, their infant's early years, in the chance that they will be successful in school. Well, I don't agree with Canada or Paul Tough that no research is necessary. The very primitive information that Canada was able to apply about the importance of child-directed speech is certainly correct. And certainly we do know something. But I think parents could be so much better informed of the amazing events that are going on in the brains of their infants based on research of the type that will be going on here and that's been going on in cognitive neuroscience during the last 15 or 20 years. In this talk, I'm going to deal with 3 areas. First, language, literacy, then the processing of number, and finally, the area of attention which is involved in the regulation of other brain networks and which allows the infant to achieve the ability to control their emotions and control some aspects of their behavior. Let me start with literacy. We usually think of literacy as being initiated when the child begins the first grade and starts to learn to read. But actually, the process goes back to the earliest days of infancy. The infant comes into the world with the ability to discriminate, to show discrimination or differences between the phonemes in all the world's languages. And in the work of Pat Kuhl, it's become clear that even before the child, the infant, begins to babble, to use language, their brains are being shaped by their speech community, so that phonemes, that is speech sounds that are the constituents of speech, that are in their own native language and used by their native language. For example, in English, the distinction between ra and la are organized into separate clusters, allowing a very easy discrimination between them. While in the Japanese infant, this discrimination is lost because it doesn't matter. It isn't important in their language. A single unit stands for the whole thing. This work of Pat Kuhl goes on beyond this. It turns out you could actually preserve the phonemes of another language by having the infant tutored by someone in that language. So she showed that in English-speaking infants in Seattle, a Mandarin tutor could preserve Mandarin, the distinction between Mandarin phonemes that normally would be lost around 10 months. So actions early in life can change the shaping of the phonemic basis of the language by making some phonemic discriminations very difficult and by solidifying the phonemic discriminations in your own language. Moreover, some work using this methodology, electroencephalography, that is, recording brain waves from many, many different electrodes on the scalp. You can do this in infants. It's going to be done at the Basque Center. You can do this in children and in adults. And you can see the ability of the infant or child to discriminate between phonemes. For example, by repeating the same phoneme over and over again and then switching to a new one. In the person who is going to develop a very strong language, switching to the new phoneme will produce a distinctive pattern of electrical activity called the mismatch negativity. And in control subjects, those chosen at random from a subject, from the population, the mismatch negativity is very strong. But for infants who, because of their parenting, are at risk for failure in language, that mismatch negativity disappears. In this work of Liitonen and also of Malfis. So we can look at the infant brain with the methods currently available and see how successful the language community has been in shaping the phonemes. Moreover, people who are successful in having the phonetics, the phonemes shaped correctly, will do well when they learn to read several years later, while those who fail will do poorly. So this recording from the electrical activity of the brain is predictive of future success in acquiring the skill of literacy. You may know that a number of years ago, EEG of this type using brainstem evoked potentials had turned out to allow us to tell that infants at a very early age were deaf, not hearing. They provided an early clue as to the infant's ability to hear. That allowed interventions so that infants who were born deaf couldn't really test them in the conventional ways, but using these tests, could be given interventions such as early sign language or other methods of allowing them to communicate. We can see a time when research will allow us to show similar problems in the phonemic structure, diagnose likely difficulties that might take place in reading down the road, and intervene in a way that might help the child when the time to come to reading occurs. And cognitive psychologists, some in this room, have been developing models of tasks like reading for many, many years. And this is a simple one that looks at the spelling and phonology and its connection to meaning. These components become places or ways at looking at underlying brain mechanisms. So, for example, it's possible to see that there are two parts of the posterior part of the brain near the occipital lobe which are important for reading. One up here in blue is an area where where the phonemes matter so that a written word can be put into its phonological form. And an area down here I'll talk about a little later called the visual word form area chunks the letters into a unit. So if you have a long word, if it was nonsense material, you might have to scan it letter by letter. But if it's a word in your language, it is now treated as a unit. These two areas of the brain operate automatically in skilled readers and then are interfaced to areas more anterior, which involve attention, abstracting meaning, and other higher level aspects of language. For a child who has difficulty in learning to read, this area of the brain, this phonological area, is not activated when he reads words. He may struggle very hard, but the area of the brain that would normally package the letters into a sound doesn't operate properly. It is, of course, possible to intervene with methods for building the skill of analyzing letters into their sounds. So in alphabetical languages like English, a program called word building is one of many programs, phonics-based programs, which attempt to intervene to help the child learn to read by helping them get a hold of the sound pattern. So children who early on in infancy did not build up the correct phonological phonemes structures can now be helped to carry on the reading task in any case. And this can be computerized as it is in the word building form. And McCandless and Beck and their associates carried out 20 days of training children who were dyslexic, who failed to have the activation of this phonological area. And they showed that after 20 days of intervention, there was a great improvement. You can see all these parts for the intervention are all improving. You can see that in all the different word attack and comprehension and so on. Whereas the control group, some go up, some go down, but on the average, there's very little improvement. And prior to going through this intervention, the dyslexic readers simply didn't activate this area that we think of as important for the phonology of the language. They weren't able to read, they didn't activate this area. They might overactivate frontal areas. That is, they might struggle very hard, but that didn't really work. And, but after training with the word building program, you can see there's quite a bit of activity in this fMRI image in this area, and even some down here. And so the child not only shows behavioral effects of better reading skills, but in a sense they can now decode. They can now sound out words and read correctly. However, they usually aren't fluent readers. That is, the phonological codes provide a skill in decoding, but they are not sufficient to make the child a fluent reader. And we have a clue as to why that is, because as I mentioned before, there's a second area of the occipital lobe, often called the visual word form area, which chunks letters into a unit and gives the child the chance to deal with the whole word rather than letter by letter. Stan DeHaan and his associates had studied an unusual patient, a patient who had a lesion a stroke which separated the right hemisphere from the visual word form system of the left hemisphere. That is, although if the word went directly to the left hemisphere, they could read it fluently, just as they did before the stroke. If the word went directly to the right hemisphere, that is, if it was at the left of fixation, and had to be transported to the visual word form area, they couldn't read it at all. They only could sound out each letter painfully and put together the overall word. So here we see in this patient something about the importance of this visual word form area in automatically allowing chunking of letters and fluent reading. For those of you who know the struggle between phonics and look-say methods in education, it's, I think, quite amazing to see laid out in the brain two separate areas. One of them is subject to tuition by phonics instruction very well. The other one, not so well. And we don't necessarily know the very best way to build the visual word form area, but of course long continued effort at reading is probably an important part of building this area and becoming a fluent reader. So the brain activity here gives us a story about how to proceed with the tuition of reading, which I think will be helpful to many, many teachers. Of course, many children, I guess many especially in this area of Spain, have more than one language. And recent years have brought about a rather surprising finding about multilingualism. A number of investigators, starting with Bialystok in Canada and dealing with French-English bilinguals, and here also in Minnesota, Carlson and Meltzoff, have studied children who learn more than one language. And they have found and compared them with controls who are matched in as many ways as possible, same IQ, same socioeconomic status, and so on, and showed that those children who have more than one language appear better in tasks which deal with what I will call self-regulation, such as the ability to resolve conflict between different response tendencies. So if you're instructed to stay still in your seat and listen to this lecture, but you also have a tendency to move around and talk to your friends, then hopefully your self-control or self-regulation will allow you to remain quietly in your seat. Very important skill I'll talk about a bit more later. But apparently from these studies, bilinguals do better than monolinguals in this skill. This is a very important potential finding. It needs more work to be certain that it's correct. But at this very moment in the United States, many states, counties, and school districts are flying the flag of monolingualism, saying, well, our state should be purely English, just as psychologists and linguists begin to show that the bilingual brain has better chance at self-regulation, a skill that's probably badly needed in much of America. The more distant the two languages are from each other, some preliminary research shows by Barbara Lust at Cornell, comparing European languages with people who are bilingual in European Asiatic languages, which differ very greatly, showed that the more different the two languages, the better the self-regulation. A very intriguing potential finding. But like many of the things I tell you, of course, more research is necessary. So I'm both telling you things that I think are realistic aspects of the current scene which can be applied, but also which would benefit from the work of the Basque Center and the many other places in the country that are hoping to study and are studying these questions. Literacy. I finished. Let's talk about numeracy. Now you might think, oh, well, language certainly goes back to infancy, but number? That is, would we expect number to go back to infancy? That doesn't seem reasonable. That seems something that definitely depends on schooling. But this little brain is capable of simple arithmetical skills. Rather amazing. And this goes back to the work of Karen Wynn about 15 years ago when she presented her 7 to 10-month-old infants with a little puppet show. So they might see two puppets, a hand reaches in and deposits a third puppet, the screen goes up, and there might be three. If you're with me, that's a correct answer. Or there might be one. That's an error. And the infants looked longer when there was an error. Now, one of the things that psychologists have learned a lot about, maybe because of our own behavior, is the detection of error. It's a property of an important part of what I will call the high-level executive attention system that's involved in self-regulation. So Andrea Berger and her colleagues, which included me, wanted to find out if the brain system that the infant used to detect error was the same as found in the adult. That way we could say this high-level system might be there in infancy. And in fact, we repeated the experiment that Karen Wynn had done, but this time the infant wore a set of 128 electrodes, and we looked at the brain waves, the sum brain waves, when the answer was correct and when the answer was in error. On the left are the adult brain waves, and you can see by about 250 milliseconds, the error trials become negative, that is further down, than the correct trials. And the same is true of the infants, 7 months old. They're about 50 milliseconds slower, but they're exactly the same set of frontal midline electrodes as found in adults. And those electrodes, we know, represent activity in a part of the brain which is part of this high-level attention system called the anterior cingulate gyrus. So we were able to show that infants were not only carrying out arithmetic, but recognizing errors that were presented to them in pretty much the same way as the adults were. And in fMRI work, Stan DeHaan has shown the particular areas on the left and right hemisphere in the parietal lobe which are important for carrying out the skill of understanding number. And what I mean by understanding number is relating the number, the symbol, whether it be presented in in Arabic numerals or spelled out or spoken, to the quantity. He calls this area of brain the number line, as if in the parietal lobe there was laid out an analog representation of the number. In fact, at least children of a few years old, in fact, use exactly this same mechanism if they're asked whether a dot pattern is greater or lesser than another dot pattern. And so this mechanism is a crucial part of the understanding of number. As adults, it's hard to know, it's hard for us to realize how difficult it is to have a symbol stand for a quantity. But this accomplishment is crucial for elementary school education. And Robbie Case has shown that if you take children who are at risk for failure in the first grade number system because they really don't know what a number is, and give them appropriate training, that you can avoid that horrendous early failure. And Stan DeHaan and his colleague Anna Wilson have developed a computerized version of this principles that used by Robbie Case to instruct children in early magnitude representation. In case you want to see it, you can see these programs either on this website or on Stan DeHaan's own website and get an idea of what they're like. This website would also be an appropriate one to look at some of word building. That is the program that Beck and McCandless used to train children in phonology. Interestingly enough, the brain mechanisms involved in dealing with number are culturally specific. This is a little bit of a surprise. Throughout the world, most cultures are now using Arabic digits. For example, both the Chinese and the American culture use Arabic digits as a way of indicating, as a symbol to indicate particular quantity. And in this study by my colleague Yiwan Dong, both Chinese speakers and English speakers were asked whether a particular Arabic digit, they were quite familiar with the digits, a particular Arabic digit was below or above 5. So they got a 6 and they said above, and they got a 3 and they said below, and so on. Most of the time they're correct. We know the circuitry involved in this from the work of DeHaan in English and French speakers. But actually, the Chinese speakers used a different circuitry, even though the input and the output is identical. Very, very interesting phenomena. Why is that? Well, it could be genetic. After all, the gene pool, including the different types of genes that are had, are different among Asiatic populations than among European populations. So that's possible. It could be the language. Chinese is a very different language than English. It could be the education. We all know that Chinese schools and other Asian schools tend to produce students with better arithmetic skills than most, at least most U.S. schools, perhaps also true here in the Basque Heartland. Well, we don't really have the answer to this difficult question. We don't really know whether this is the education, whether it's genetic, whether it's language, or what. We don't know, for example, whether we could train U.S. students to use the neural pathways, including the premotor area, that are used by the Chinese students. But you can see why places like the Basque Center are crucial for continuing research in this area. We may be able to make a breakthrough that could help many, many people struggling with early arithmetic and the mathematics built on it to do a better job. And this is another reason why I know, and I believe Obama knows, that research is necessary in this field to continue. I want to shift to something I think every parent knows is an important part of infancy and early childhood. That is the ability of the child to regulate their own behavior, to be able to comfortably sit in a long and boring lecture, perhaps even looking interested. This is a very big skill all students need. And we believe there's a brain network that is extremely important in this kind of self-regulation. It is a network which is part of the brain's attention system. And we now believe that it is present even early in infancy, as early at least as 7 months. And it involves a number of brain areas, but most important is this green triangle in the anterior cingulate gyrus. This is an extremely important node of this brain network that interacts with other brain areas to give priority to certain activities. A very simple way to activate this brain area is to present the subjects with a very simple task. Children, monkeys, adults, brain-injured people, they can all do this task. The task is to decide whether the central arrow points to the left or right. If it points to the left, you press the left key. Points to the right, you press the right key. But the arrow, the central arrow, is surrounded by flankers which may be congruent, point in the same direction, or incongruent, point in the opposite direction. Now, surprisingly enough, if I subtract the reaction times for incongruent trials from those and subtract from those the congruent trials, I get a number. And that number has to do with your ability to resolve conflict. That number turns out to be related in childhood to parental reports, questionnaire reports, of the ability of their children to control their emotions and behavior, to come to the dinner table when the bell rings, to quiet themselves if they should hurt their knee, and so on. These scales, developed by my colleague Mary Rothbart, are reported by parents in early childhood and infancy, and later on self-reports. For example, in adolescence, the person reports themselves. And all through childhood, the small difference between congruent and incongruent reaction time and the parent reports of effortful control are correlated. Moreover, adolescents' reports of their ability to control their behavior and emotions are correlated with the size and activation of parts of the dorsal and ventral anterior cingulate gyrus, just as you would expect if the story I'm telling you is even partly true. These are not trivial matters. It may be that pressing a key when an arrow turns to the left seems a little trivial, and parents' reports of your ability of their children to control their behavior might seem a little suspect, but together they predict very important landmarks of childhood. For example, the ability to delay reward, go through 4 years of college waiting for that bachelor's degree, or the lecture waiting for the tour of the aquarium. Also, theory of mind, that is, the ability of the child to appreciate the mental activity of other children, and the development of conscience, that is, of pro-social behavior, the ability to avoid lying and cheating when the experimenter gives you a chance. And outside the laboratory during adolescence, effortful control and executive attention, that is, the difference between congruent and incongruent reaction times, are negatively related to antisocial behavior, for example, truancy. So these are important landmarks of childhood, and on the one hand, we can measure them by a simple reaction time task, very easy reaction time task. On the other hand, they are obvious to parents and to the people themselves. And we know that the parts of the anterior cingulate have different connectivity. This more dorsal part of the anterior cingulate, that is the kind of stippled version, that's connected to parietal and frontal areas important in cognitive activity. Whereas this more ventral part, which is shown in black, is related to the amygdala and other structures related to emotion. So if I give you the instruction to pay attention to the slide, and you shift attention to the slide and give that priority, my voice tends to be a little quieter. I try to avoid that problem by speaking so loudly, but nonetheless, you are now tending to the slide. That visual information is amplified. The anterior cingulate is coupled to the visual system. If you switch to my voice, it's now coupled to the auditory system. If you're asked not to become emotional when you see a positive, like one of the people on the beach this morning, it was a very positive stimulus. If I was supposed to not become emotional, in order to avoid having an emotional reaction, activity in the ventral part of the anterior cingulate becomes coupled to the limbic system. Or if it's a negative stimulus, a frightening stimulus, it becomes coupled to the amygdala. So there are experimental studies showing the connectivity of these regions with respect to controlling other areas of the brain. Now, the advantage of having a little reaction time task to measure self-regulation is that you can look at the area of the brain that is active when that reaction time task is carried out. Turns out to be, at least in part, this area of the dorsal anterior cingulate gyrus. And you can ask, what are the brain networks involved? What are the neurotransmitters or neuromodulators involved? In this case, it's dopamine. And then you can say, what are the genes that shape the receptors and other parts of that modulation network? So you can now say, well, let's look at dopamine-related genes that have different flavors. That is, that are different in one person than another. We all have these dopamine genes, almost everyone, but the flavors, the alleles, are slightly different. So, for example, this dopamine 4 receptor gene might in one person have a particular part that's repeated twice, in another person repeated 7 times. And it turns out that if I put people in 2 separate groups, the reaction times to resolve conflict are different between those groups. So this allows one to talk about the genetic differences that might account for individual differences in your ability to resolve conflict. And this slide is simply suggesting the links between the underlying genetic activity, which produces a protein, and the brain network, which is involved in this case in high-level attention. Here's the slide that deals with the dopamine 4 receptor gene. As I say, there's a part of the gene that this 48 base pair that can be repeated 2, 4, or 7 times. The 7 repeat allele of the DRD4 gene has 2 what might seem to be contradictory properties. It's overrepresented in children that have attention deficit hyperactivity disorder, that is, who tend to have difficulty maintaining attention, and it is undergoing positive selection during the last 50,000 years of human evolution. In our study of children of 2 years, we genotyped the children, so we knew what alleles of the 7 repeat, what alleles of the dopamine 4 receptor gene they had, and we measured their interaction with their parents. Now, these are all normal parents. They interacted well with their children, but some were more supportive, some gave the child more autonomy, and so on. And we used a scale developed by the National Institute of Health to rate the parents and then to distribute them as to whether they were in the top half, highest quality parenting, or lowest quality parenting. And I'll illustrate our finding this way. In children up here is impulsivity, which is one of the temperamental characteristics of ADHD. All these children are normal. They're 2 years old. They've never been diagnosed with any disorder, but some of them are more impulsive than others. If they had 4 or 2 repeats and didn't have the 7 repeat, the quality of the parenting didn't matter. But if they had the 7 repeat, look at this, the quality of parenting had a huge effect on their behavior, on their perceived impulsivity. And we believe this might be one way of thinking about the relationship between genes and experience. You all hear, well, is it nature or is it nurture? Well, if you're following the current newspapers and magazines, you know everyone says it's an interaction. But then usually they go on to talk about one or the other, whatever they're studying. Here we see something that could mean that genes with particular alleles undergoing positive selection do so because they make culture more influential on the child's behavior. Now here culture is, the surrogate for culture is parenting. Parenting represents the culture to the child. And you can see that if the child has the 7 repeat allele, that can make them very much avoid over-impulsivity. Now, allowing the culture to shape behavior is a sure bet for reproductive success and therefore positive selection in evolution. Now, is it reasonable that something like the dopamine 4 receptor gene and its influence on dopamine could make parents more or less influential? Well, the anterior cingulate is part of the systems that involve reward and punishment. The more successful, the more efficient these systems are, the more likely the parent will be successful in dealing with the child, influential on the child's behavior. Of course, it's just one gene and one set of behavior. It's not everything, but I do think it shows the potential for research here. Not only in laying out the neural networks that are important in crucial things like literacy and numeracy and self-regulation, but also for letting us understand how genes and experience work together to shape those neural networks and to build the child that we come to observe in later development. Well, if parents are so influential, you might wonder, could we be influential? Could we actually train this self-regulation network? When Chara Rueda, Mary Rothbard, and I entered into this question probably about 7, 8 years ago, we thought it was a very risky possibility. But nonetheless, with the help of many other investigators, we did develop a training program, 5 days of training. And that program did produce a significant change in the brain network underlying self-regulation. We were very excited about this. In the interim period, many of the last 5 to 7 years, lots of other programs have come along, and many of them have also shown important influence on the subject's self-regulation and attention. For example, a whole curriculum called Tools of the Mind, which is used in preschool, has shown very great improvement in self-regulation. And Turkel Klingberg and his program CogMed has shown attentional improvements in childhood as well. So what seemed like a little bit far out possibility now seems like something that is established in one sense. We are able to make some changes, but these have never been followed out over long periods of time. We don't know if this helps the child in school. We don't know if they will our idea was that even a little change prior to the start of school might lead to better success in the early grades and therefore spiral up and lead to a more successful child. Well, of course, more research is necessary. Many centers are needed. The center here, I'm sure, will make a major contribution to these issues. And in this lecture, I've tried to give you a feeling of why the citizens of a region like this, through their government, might want to support a center for studying how infants and children develop, because they are concerned with the children and they wish them to be more successful. I don't want you to think that everything ends in infancy. There's hope for all of us at whatever age. So I very much appreciate your attention. In summary, I've tried to give you a little feeling that there has been progress made in the study of the infant and child development in the areas of literacy, numeracy, and attention. But much more needs to be done. Research centers are crucial, and I wish every success to the center here in developing these topics. Thank you very much. Sure, be happy to.
Si hay alguna pregunta, él está encantado de responderla.
The question is, are there any studies of multilingual children and effects on the brain? And there are such studies looking at the degree of overlap between the languages in various parts of the language network. As you might not be surprised to know that there's more overlap the earlier the languages are developed and the more similar the languages are to one another. But there's much that's unknown. For example, we don't know if the self-regulation that's been shown with bilinguals over monolinguals continues to escalate. It might, or it might not. So these are definitely subjects of important areas for research.
Bueno, muchas gracias. Antes de terminar, el viceconsejero de Educación y de Universidades va a clausurar el acto. Que sepan que este acto no es único, es el comienzo de una serie que hemos llamado Brain Talks, que pretendemos pues ofrecer para el público en general, coincidiendo con distintos eventos que llevará a cabo el Bass Center on Cognition, Brain and Language. La información aparecerá en la web y también en los periódicos a su debido tiempo.
Una brevísima intervención. En primer lugar, para agradecer al profesor Posner su interesantísima conferencia. Thank you very much, Professor Posner. Y también para agradecer a todas las personas que han acudido a esta conferencia, puesto que para este centro dedicado a las neurociencias y su interfase con el lenguaje, este es un momento muy especial. Aunque ya hace unas fechas comenzó su andadura, representa una de esas apuestas de país que se están realizando para cultivar aquellas áreas en las que nos gustaría que se nos conociera. El País Vasco ha sido durante mucho tiempo conocido por su laboriosidad, por su capacidad tecnológica, por sus industrias, queremos que ese conocimiento nuestro continúe siendo verdad a través del talento de nuestras personas, y qué duda cabe que seleccionar adecuadamente áreas de investigación en la frontera del conocimiento, contando con investigadores excelentes, adecuadamente conectados con las redes que internacionalmente existen alrededor de estos temas, pues tienen una importancia crucial para poder jugar en esa liga importante de los países desarrollados. Y en este caso, pues yo creo que hay que agradecer al profesor Carrera y a toda la gente que trabaja en el BCBL el esfuerzo que están realizando, y también esa capacidad de convocatoria a través de la cual pues una serie de expertos van a continuar lo que haya empezado ante un público más general, mañana en un público más especializado, creando ese hito de un primer encuentro alrededor de esa conexión en un área tan compleja pero con tanto futuro, cuál es la conexión entre lo que vamos sabiendo del cerebro humano y sus interacciones con todo lo que tiene que ver con la lingüística, con el lenguaje. En una sociedad en la que además yo creo que tenemos que ser capaces de reivindicar que el contar con más de una lengua, y ojalá pronto pues seamos capaces de, muchos de nosotros, ser capaces de utilizar una tercera o incluso una cuarta, es una oportunidad, es una riqueza, y lo que no debe ser nunca es un problema. Eskerrik asko eta hurrengo arte.